Hello, I'm Anand Jain from Hanumangarh, Rajasthan. Welcomes you to your favorite Shridevi Classes YouTube channel where we inculcate interest and confidence in science and engineering subjects. We also wish a very happy New Year 2023. May your effort and deeds bring great success and lot of happiness in your life. Today in our class 12th physics playlist, in the chapter Electric Circuit, we'll discuss chemical cell and we'll study what is EMF of a cell, what is internal resistance of cell, and how questions are framed on these two concepts of EMF and internal resistance. Let's start. Chemical reaction in some substances can produce electrical energy from chemical energy, and these devices are known as cell. Cell are of two types. One is called primary cell, where chemical reaction is a irreversible process. It's only a one-way reaction and we can't recharge these cells again and again. Whereas secondary cells can have facility of recharging as chemical reaction is reversible and we can produce chemical back in fresh form by supply of electrical energy. Lead acid cell is one such cell, but the first historic cell is developed by Volta in the year 1801 and that cell is known as Voltaic cell. In Voltaic cell, in a solution of dilute sulfuric acid, we put two electrode. One is of copper that become positive electrode anode and the other one is electrode of zinc that become negative polarity electrode or cathode. Ionization of dilute sulfuric acid H2SO4 take place and in electrolyte we got hydronium ion H plus 1 and sulfate ion SO4 negative 2 electron charge. These ions have different affinity about two electrodes. Positive H ions moves towards copper electrode and sulfate negative ion attracts towards zinc electrode. At zinc cathode, zinc electrode receive two electron from sulfate ion and zinc chemically react with sulfate and form zinc sulfate that get dissolved in H2SO4 solution. So zinc is consumed and per atom of zinc produce two negative electronic charge on zinc electrode. Due to that, the potential of zinc electrode with respect to electrolytic solution get reduced by an amount of 0.62 volt. At the same time, positive H ion moves towards copper electrode, takes electron from it and produce 1 unit positive electronic charge per atom. Two H such atom after neutralization from copper electrode react together and form H2 gas that escape out from H2SO4 solution, and in the process copper electrode with positive potential has a potential difference with respect to electrolyte equal to 0.46 volt, and when the potential difference between two electrodes copper and zinc achieve 1.08 volt level, the chemical reaction stops. When we connect external component in circuit, then electrons from zinc electrode passes to copper electrode in external circuit and we assume that current in opposite direction of electron flow moves in circuit from copper to zinc in external circuit. That charge movement reduce potential difference between copper and zinc and restart chemical reaction again, and this process will continue until whole zinc get dissolved in solution, and after that we have to replace zinc rod and the solution, then only we can get electrical output energy. This first primary cell, Voltaic cell, have two problems. One, due to impurity in cathode zinc electrode that we call local action, and the second is accumulation of H ion and H2 gas near copper electrode that we call polarization. Local action in cell occurs when we place zinc cathode in electrolytic solution without external circuit connection. Local action is caused by the presence of impurities in zinc cathode such as copper, iron, tin, carbon and or lead. Now these impurities acts like anode and form minute local cell. Due to that cell action, negative sulfate ion react with zinc, form zinc sulfate and give two electron to zinc electrode. At the same time, impurity attract H ion and give those electrons to H ions and neutralize H ion to form H2 gas, and in the process zinc get dissolved and consumed in solution without any electrical output. So this is wastage of our cathode material by local cell action. Now this can be eliminated. If we are not using cell, we should place cathode out of electrolytic solution, or we can put a thin layer of mercury over zinc Such amalgamated zinc rod can stop local action as mercury top layer cover impurities and they can't react with electrolytic solution, but zinc dissolve in mercury comes on outer layer and react with electrolytic solution. So amalgamated zinc rod can stop local action. Polarization is caused by concentration of positive H ion or neutral H2 gas near anode material as copper in voltaic cell. Neutral H2 gas is insulator in nature and positive H ion repel other positive H ion. So this concentration restricts free flow of ion in electrolytic solution and that increase internal resistance of cell. Due to increased internal resistance, more voltage drop takes place internally and external terminal voltage and output current of cell reduces. To control problem of polarization, a depolarizing agent which is rich in oxygen and act as an oxidizing agent is used near anode electrode so as to convert hydrogen into water, such as manganese dioxide MnO2 used in Laclanche cell and copper sulfate used in improved version of Voltaic cell called as a Daniell cell. Now these depolarizing agents supply free oxygen to hydrogen and form water. So accumulation of hydrogen gas and hydrogen ion is reduced and internal resistance of cell remain low during operation. Daniell cell shown here is an improved version of Voltaic cell. All three, anode material copper, cathode material zinc and electrolytic solution dilute sulfuric acid, are same in Voltaic cell and Daniell cell, and EMF depends upon these three material of anode, cathode and electrolyte is the same 1.08 as that of Voltaic cell. The anode copper is taken as vessel for cell. To stop polarization, depolarizing agent copper sulfate is used near anode copper vessel, and to stop local action, amalgamated zinc rod is used. In this cell, EMF value 1.08 volt remain constant irrespective of current supplied by the cell. So this Daniell cell is used as a standard cell and its EMF is 1.08 volt. Another important primary cell is Laclanche cell, which use carbon rod as anode material, amalgamated zinc rod as cathode material, and dilute ammonia chloride solution as electrolyte. MnO2 is used as a depolarizing agent. To increase conductivity of MnO2, carbon powder is added in it. Now all material of anode, cathode and electrolytic solution are cheap. So this Laclanche cell is commercially used in our domestic and other applications. Its EMF is also very good, 1.5 volt. For portable applications, in place of liquid ammonia chloride solution, we use a dry version of Laclanche cell. In dry Laclanche cell, central carbon rod become anode positive electrode and zinc vessel become a negative cathode electrode. Electrolytic solution ammonia chloride is absorbed in sawdust and ammonia chloride paste is used as electrolytic solution, and to increase conductivity, a little amount of mercurous chloride is also added in it. For depolarizing action, we use manganese dioxide as oxidizing agent, and to increase conductivity of MnO2 powder, we add carbon dust in it. Domestic cell used in clocks, transistors and other electronic devices is this dry version of Laclanche cell. Electromotive force EMF of a source is defined as terminal voltage or that potential difference which is available on terminals in open circuit condition when cell is not supplying any current and there is no voltage drop in internal resistance and all source EMF come across terminals. The value of EMF depends upon material of anode, material of cathode and the material of electrolytic solution. Due to chemical reaction, anode got a certain positive potential with respect to electrolyte and cathode will have some negative potential, and that generate potential difference between anode and cathode, and that is EMF of source. For current flow in cell circuit, EMF has to work against both external resistance as well as internal resistance, and we define EMF as that amount of work done in joule in circulating 1 unit positive charge both across internal resistance and external resistance. EMF of cell is very important. Equally important is internal resistance of cell in deciding performance of cell in electric circuit. In electrolytic solution, due to collisions, opposition to the flow of charge carriers takes place, and charge carrier in electrolytic solutions are both free electrons as well as both positive and negative ions, and most of the charge is carried by these positive and negative ions only in electrolytic solution, and opposition to this flow of charge carrier in solution is called internal resistance of cell. And internal resistance of cell depends on conductivity of electrolytic solution, and concentration of solution and operating temperature decides conductivity of electrolytic solution. Dilute solutions having lesser amount of material have better ionization and higher conductivity, and higher temperature increase mobility of ion and increase conductivity. So dilute solution and higher temperature has lower internal resistance. Now the separation between positive and negative electrode decide length of current flow, and internal resistance is directly proportional to that separation. Now the immersed area of electrode plates inside electrolytic solution decide cross section area of current flow, and internal resistance is inverse of area of cross section. Higher the immersed area of electrode, lower would be the internal resistance. Internal resistance also depends upon defects of cell such as polarization. Polarization increase free movement of ions and internal resistance, so we use depolarizing agent to reduce polarization effect. Internal resistance also depends upon current magnitude supplied by the cell, as this increase amount of polarization. In any electric circuit, chemical cell is a series combination of source EMF and internal resistance. When cell supply current to external circuit, voltage drop in internal resistance takes place, and this voltage drop increases with increase of current supplied by the cell, and internal resistance voltage drop is subtracted from source EMF to get terminal voltage across load resistance, and higher the current supplied by the cell, lower would be the terminal voltage available across load. When a cell, a series combination of source EMF and internal resistance, is connected to external load resistance, then for current flow, EMF source has to act against both external resistance and internal resistance, and current got this expression: EMF acts across both internal resistance as well as external resistance. The voltage which is available at the terminal of cell at load condition is known as terminal voltage V, and terminal voltage V is across load resistance R, and current is given by this relation. To find out voltage across internal resistance, the two terminal of internal resistance can be imagined, and if we move in this circuit, it is rise of E EMF and drop of V terminal voltage. So voltage across internal resistance is E minus V, and voltage divided by resistance become expression of current in internal resistance. Since internal resistance and external resistance both got the same current flow path, are in series, so the current is same. So this blue framed and yellow highlighted relation is very important for cell analysis, and one can remember this relation by this figure. EMF act across both internal and external resistance, terminal voltage is only across external resistance, and the voltage across internal resistance is E minus V. Three value of external resistance are very important for examination point of view. One is external resistance is 0. This condition, when two terminal of cell are connected together by a thick wire, external resistance becomes 0, is called as short circuit condition of cell, and in short circuit condition the terminal voltage V becomes 0, and when V is 0, you cannot evaluate 0 by 0 condition by V by R relation, but you can analyze circuit current as E by R, as when terminal voltage is 0, the whole EMF will come across internal resistance and produce maximum E by R current in cell circuit. So in short circuit condition, terminal voltage is 0, but the current is maximum and is given by EMF to internal resistance ratio. Lead acid cell got lower amount of internal resistance, so they have a very high amount of short circuit current, whereas Laclanche cell got considerable amount of internal resistance, roughly of the order of 1 ohm, so its short circuit current is not that high. Another important position of cell analysis is when external resistance become infinite and two terminal of cell are open circuited. In open circuit condition, there is no current flow, so current become minimum 0, and there won't be any drop in internal resistance, so whole source EMF come across terminals. So we say EMF of source is that terminal voltage which is obtained in open circuited conditions. In the circuit of cell, source EMF has to act across both load resistance and internal resistance, and current is given as EMF divided by total circuit resistance. The voltage across load resistance or across cell terminal is known as terminal voltage V, and current can also be written as V by R. And the voltage across internal resistance is E minus V, and current can also be expressed as E minus V over R. So we have seen that EMF act across both external resistance and internal resistance and produce current flow I in the series circuit. The voltage of load resistance is terminal voltage. We can express terminal voltage as difference of source EMF and voltage drop in internal resistance. So voltage of load resistance with current flow I decreases as load current increases, as increased load current increase voltage drop in internal resistance. So terminal voltage and load current has a drooping linear characteristic as represented by this relation or this graphical presentation. The product of terminal voltage and load current is load power, and load power in load resistance R can also be written as per Joule's law as I square R, and I is E upon capital R plus small r, and when square of current is done and multiplied with R, we got this expression of power. And if internal resistance is variable, the maximum power in load resistance will take place when load circuit current is maximum, when internal resistance is 0. But if external resistance is variable, then this external resistance comes both in numerator and in denominator. And interesting fact is, during open circuit, we got maximum load terminal voltage, but current is 0. So there is no output power in open circuit condition. Similarly, in short circuit condition, we got maximum current in cell circuit, but there is no load voltage across load resistance, as load resistance is 0 in short circuit. So in that condition also power output is 0. So in open circuit condition, only voltage is maximum, power and current is 0. In short circuit condition, only current supplied by cell is maximum, and both load voltage and load power is 0. For maximum power, this variable load resistance should have value equal to internal resistance of cell, and when the two are equal, we will get terminal voltage of load equal to half of maximum value. Maximum terminal voltage is equal to source EMF in open circuit condition, and for maximum power condition, when load resistance is equal to internal resistance, the load voltage become E by 2. Similarly, when load resistance is equal to source internal resistance, the load current become half of maximum short circuit current, and maximum power product of load voltage and load current become E square by 4R. So maximum voltage occurs when load resistance is infinite, maximum current occurs when load resistance is 0, and maximum power occur when load resistance is equal to internal resistance, and maximum power is E square by 4R. Practice of following 4 numerical example will increase both subject clarity and scoring ability. We have given terminal voltage and load current characteristic of a cell in this figure, and without current in open circuit condition, terminal voltage is 3 volt, and short circuit condition has 0 terminal voltage and maximum 6 ampere current. We have to find out terminal voltage and current of this cell when load resistance is 4.5 ohm, and we have to find out maximum power condition for this cell. So we know in open circuit condition, when current is 0, the terminal voltage obtained as 3 volt from this characteristic is source EMF. Now in short circuit condition, when terminal voltage is 0, whole source EMF come across internal resistance, and short circuit current is E by R. Now the value of E is 3 volt, short circuit current is 6 ampere. We can find out internal resistance of source as EMF upon short circuit current, and it comes as 0.5 ohm. So this cell got EMF 3 volt and internal resistance 0.5 ohm, and when external resistance R is connected to this circuit, the source current is given by this formula. EMF is 3, internal resistance is 0.5 ohm, and external resistance is 4.5 ohm, and calculation results in load current equal to 0.6 ampere. With this 0.6 ampere current in 4.5 ohm resistance, the terminal voltage V is equal to IR is current multiplied by load resistance equal to 2.7 volt. This 2.7 volt can also be obtained as IR drop with 0.6 ampere current in 0.5 ohm internal resistance is 0.3 volt, and EMF is 3 volt. So when IR drop 0.3 volt is subtracted from EMF 3 volt, we will get terminal voltage E minus IR equal to 2.7 volt. From the cell characteristic, open circuited voltage is source EMF 3 volt and short circuit current is 6 ampere, and we know internal resistance of cell is open circuited voltage and short circuit current ratio, and it comes as 0.5 ohm. So this EMF source got 3 volt EMF and 0.5 ohm internal resistance, and when variable load resistance is connected, connected, the maximum power in load resistance will take place when external resistance is equal to internal resistance 0.5 ohm, and in that case when load resistance is 0.5 ohm, the current of circuit become 3 ampere, which is half of short circuit current, and half of voltage of source EMF drops across internal resistance, and half of this EMF 1.5 volt will become terminal voltage, and product of terminal voltage and load current become our maximum output power 4.5 watt in this case. A cell supply 3 ampere load current for a external resistance of 1 ohm, and the same cell supply 2 ampere current when load resistance is changed to 2 ohm. We have to find out cell current when external resistance is 3 ohm. Let the EMF of cell is E and internal resistance of cell is small r. So when 1 ohm external resistance is connected, source current is E divided by internal resistance and external resistance 1 ohm, and current is given 3 ampere. This become our first equation. Similarly, for load resistance 2 ohm, current is EMF divided by internal resistance and load resistance, and it is given 2 ampere. So this become our second equation. Now two linear equation in two variable can be solved. EMF from first equation is 3 times internal resistance and 3, and from second equation it is 2 times internal resistance plus 4, and when we simplify it we will get internal resistance value 1 ohm, and when internal resistance 1 ohm is substituted we got EMF as 3 plus 3 6 volt. So source EMF is 6 volt, internal resistance is 1 ohm, and when external resistance 3 ohm is connected, the total circuit resistance become 4 ohm, and current in 3 ohm external resistance will become 1.5 ampere. When an ideal voltmeter is connected across cell, this voltmeter of infinite resistance will measure cell voltage without drawing any current, and it is 2.2 volt, and this open circuit voltage is source EMF. When a load resistance of 5 ohm is connected across this cell terminal, the voltmeter reading drops to 1.5 volt. We have to find out internal resistance of cell. So EMF in this case is 2.2 volt, terminal voltage with load resistance 5 ohm is 1.8 volt, and we know when terminal voltage and load resistance is given, load current is terminal voltage divided by load resistance, and 1.8 when divided by 5 ohm, it will give me 0.36 ampere current. And for internal resistance, the voltage is EMF minus terminal voltage. EMF in this case is 2.2 volt, terminal voltage is 1.8 volt, and the difference of 2.4 divided by circuit current 0.36 ampere give me value of internal resistance as 10 by 9 ohm. A cell has a source EMF of 12 volt and internal resistance 2 ohm, and it is connected to an external resistance of 4 ohm with an ideal ammeter in series and ideal voltmeter across load terminal. We have to obtain the reading of both voltmeter and ammeter. So in this circuit, internal resistance and external resistance in series will produce resultant resistance 6 ohm, and 12 volt across total resistance will produce 2 ampere current, and that would become ammeter reading. So ammeter will read 2 ampere as load current in this circuit. Now 2 ampere in 4 ohm produce 8 volt voltage, and that voltage is measured by this voltmeter. In this informative learning video, we have explained working of chemical cell and described the concept of source EMF and internal resistance. We have also explained on which parameter EMF and internal resistance depends, and we have also solved 4 exam-centric problem to improve our subject understanding and scoring ability. Our other learning video of the same playlist are equally useful in exam preparation. You can use them in your studies and share them with your friends. And if you like to join our doubt clearing online classes and need dedicated exam-centric notes, do join our membership by pressing join button just beneath. Thank you very much. Happy learning.